In the name of God, the compassionate, the merciful. This is week 3 of our series in C++ template metaprogramming. Today we are going to do some live coding, but I reckon that some of the things that I didn't manage time-wise to teach you last session is going to be used in the practice session, so I'm better just teach them before I get into the live coding. So we'll have a quick skim through some of the remaining items from the third week, and then just dive into the coding. I would like to begin by speaking about something that we call primary templates. So you probably recall the fact that there were things called template specialization that I told you about. So if you have like, let me see. Come on, no, looks like we don't have any on these slides. No, we don't have any on these slides. Okay, fair enough. So if I have a where were we? Yes, we were. If I have let's say that this this box thing that you see here on line 1, let's say that we have that, and then if I just write for example, template type name T class box of, let's say, T star, then I can specialize my class for when I pass a raw pointer to box. Now this is doable, this is good, whereas if you do this one, which you're not really specializing anything, that's not accepted as a specialization. Now, the new piece of terminology here is that the thing on line 1, is called a primary template, which you then specialize, like the one that is above line 1, right? So now well, one thing which, let's say that I change this to T star, even if I had done that, then that would have not been allowed, because template specialization is not allowed for function templates. It's only allowed for class templates and for variable templates. So for example, well, and this one is relatively new. So like what you see in here, this is a variable template called 0, which is type parameterized by a type T, and it tries to use the default constructor of the type T. Now, so you, Mikhail, not being, I didn't know that you didn't have any C++. So a lot of your confusion now makes sense to me. I thought that you did have some C++ background, but anyway, now I'm going to explain that to you a bit. Yeah, you're familiar with the term constructor, right?
Yeah.
Okay, good. Now, the constructor that does not take any parameters is called the default constructor. Right? Now,
Yeah.
when you do this, right, you're invoking that default constructor. And prior to C++ 17, the only way to invoke the default constructor was this. Now, after C++ 17, they also allowed the curly brace version, because then there is no confusion between this being a function call or a constructor call. So it's now more fashionable to use the curly brace version, even though the for backward. So you probably know that backwards compatibility is a main pillar of C++. The code that you wrote like 20 years ago should still run, compile and run, and it does actually most of the time. Now, so even though, oh, by the way, this is so even though this is a variable template, and you are allowed to specialize variable templates for the same reason that line 2 wasn't a specialization of line 1, line 8 is not a specialization of line 7, because we're just using the same old. Oh, Daniel was coming in. We're just using the same old template parameter, right? Now, hello, Daniel.
Hi, can you hear me?
Yes, we can. You've had a haircut, I guess.
Yes, I have. Sorry,
Okay.
the Wi-Fi at my place has just gone kaput again, so I'm at a cafe nearby.
Oh, I see.
Some background audible audio, and that's
Right. No problem. No problem. Thank you for taking the effort.
no worries, no worries.
Okay.
I sent a message to James, but then he called me to me through Discord, so hopefully he explained the situation.
Okay. Well, I didn't receive anything, but that's fine. No worries. You've now made it. That's all that matters. Yeah. Okay. Now, so what I was teaching before your arrival, I said that we will do a bit of the remaining slides, because I think that they will be used in the practice session. So there's no point of me leaving them to later. So that's that. And then I taught a bit of terminology. So I said that if you have like a line 1 class template, that you can specialize, for example, like line 0, which is the one above that I have scribbled myself, right, on the slide. And this is specialization. Now, a specialization is a special case for what is called a primary template. So line 1 is a primary template. And the thing is that you can only provide a specialization lexically after a primary template.
Afterwards, right?
Yes. Yeah. Now, one thing to notice is that the class template on line 1, the primary template, has no definition. It's only declared. It has no body. right? So if it's only between line 0 and line 1, which, by the way, the line 0 has to come after line 1 for it to be acceptable. If those are the only two that we have, then that means that I will only be able to use box of pointers to types, because otherwise, even though box is declared, it's not defined.
Right. Okay. So
Okay.
yeah.
So the
Specialization
primary template can be declared but not defined. But then if you do so and you provide specializations, it's only for those specializations that you can instantiate your primary template. Okay. Now, then I was telling Mikhail that specialization needs to really be specialization. So for example, if you're specializing for T here, you're not really specializing, so that's not acceptable. So box of T is just the same as the previous one, right?
Yeah,
and so is also here, right? But so even if you do that, so even if you do like replace this T with a T pointer, because this is a template, a function template, and specializations are not allowed for function templates, therefore, it doesn't really matter how you try to specialize. I mean, for function templates, no template specialization.
Yeah.
Okay. Right now, so a bit more fun. There are those things in C++ template metaprogramming which are called template parameters. We saw some of that, I think, if I'm not mistaken. Maybe not, I don't know. Now these things have a peculiar syntax. Now this F guy receives a template parameter which itself is parameterized according to type. So this is like higher higher order template metaprogramming, and if you're familiar with kinds, this is higher kinded, right? So when you have, let's say that you have a template type name T struct S, right? Now, in the light of kind programming, kind level programming, S is of type star to star, which means that S takes a type in order for it to become a type, right? Yeah. Without that type parameter, it's not still a type, right? Now, if you do template again in the angle brackets, template type name, and then let's say type name, and then the angle bracket, the first angle bracket you close, let's say struct as primed, right? Now this time S primed is of kind star to star to star. Okay. Right? Which means that the template parameter that you need to provide for S primed has itself another hole in it.
Yeah.
And this has such a bizarre syntax, as usual in C++. Now I have to tell you one thing though, that this S prime, so this is not like Haskell or Idris. So in C++, S primed is not a valid name, right? You can't prime things. Yeah. Okay. Yeah. Now let me get back to my slides without the scribbles. So this F guy takes what is called a template parameter called C, which itself, because it's a template parameter, takes a template parameter which in this context is called X, right? Now it takes a value level parameter which is C of int, a pointer to C of int, right? So that's that. Now a bit of grammar. What you here see, the keyword class. I had told you about the people in C++ gradually realizing that class and struct are really the same things, right? Now the differences between this one is private. Members of this one are private by default, and members of this one are public by default, right? Now, even though you are not allowed to use struct here, right? So if you have a if you have a template parameter, the keyword, and this is about the keyword only. It's not that you can't pass a struct, right? The keyword that you put here cannot be struct. Now C++ has another thing which I'm not teaching you here, but it's called union. Union has similarities with structs and classes that are beyond our scope at this point. But the thing is that you can't put union as the keyword here either, even though you can pass unions as the template argument. Now, from C++ 17 onwards, they began to see that, well, this is we can go for type names which are umbrella terminology for classes and structs and all that. So you're allowed to use type name here, and I personally prefer to do that one. And alias templates are also possible, even though so you can pass alias templates to here as well. It doesn't really need to be a class or a struct. So it does make sense for us to put type name here instead of class, because that would be wrongly suggestive that you can only pass classes to this F guy, right?
Yeah.
So now template parameters can also have defaults. So this container thing is itself a template parameter, right? Because it's a template parameter to this class adaptation, and the container that this adaptation takes as a template parameter, it is itself template parameterized, right? And this A guy has a default parameter, a default argument, sorry, right? Now, with that being in place, if inside the body of adaptation, I say that I want to have a variable called storage, which is of type container of int, right? I'm saying that, okay, this container of int is the same as this, because there was a default argument called myAllocator.
Okay, so
Right now, if a class or a struct takes a template parameter, it's possible for template parameters of the template parameter to depend on one another, but that has to go in order. The ones that come later can depend on the ones that come before, right? So for example, here we take a pointer to the type T as the second template parameter of buff. And T, what is T? T is itself the first parameter to, you know, the template parameter buff, right? Now this is, so this is a type, this is a pointer to that type, right? So this is a non-type template parameter. Okay, this is a value. This is not a type. Okay. Now, one thing though is that even though there are these dependencies, so dependency of this to this is available, these names do not escape the enclosing pair of angle brackets. So, for example, it's not possible within the body of the class Lexa to use the name T, because, like I said, T does not escape this scope. T is not valid outside this scope, right? Now, you can do other things to acquire, you know, and I'm not going to get into that right now. You can do other things to acquire this type, right? But that would be you know, acquiring it and giving it a name and then using it. And there is no reason for the name that you give it to be the same as T. You can call it U and then or anything and then just use it, right? Because this name T is only valid in the scope of this you know, template parameter of Lexa.
Okay, so that is parameterized by T pointed to T, which depends on T.
Yeah.
And they're enclosed in that scope. So
correct.
Okay.
Correct. So T yeah, that's right. So T point the pointer to T is still within the scope, as you just said. And you know, the ordering is preserved. So T pointer to T comes after the introduction of T, right? Now, I wish James was here, because this is the point where I could have answered one of his previous questions. So now that we are recording, I would like to get to this question of James. So James at one point asked me whether this if we do this, we can somehow acquire the type of the you know, non-type template parameter that we are providing here. Now, let me just do an undo. And we can do that in various ways, including this one. You know, this S thing, the version 1, is equivalent to templates type name T and then T something, we can name it if we want. These two versions are actually equivalent in action. What this is saying is that this non-type template parameter can be of any type. To be more precise, it has to be a value type. Right now, that's something that I'm not teaching you, but just for you to be aware of. But we don't care about the real type of it. Right now, here we're saying that, you know, it can be any type, but we do care about the name of that type. So T will be available within the body. So
yeah.
Let me see. So if I had a body here for S, T here is an available name that we can use. We could have used things like decl type for this. If we had given it a name, for example, let's say we gave it a name X, right? We could have inside this version 1 said like using T equals decl type of X, and thereafter, you know, T would have been available to us.
Okay.
Right. But in this version, you know, we have it readily available to us in the second version. Mikhail, are you following?
Yeah, I was just,
okay.
I got a message.
Oh, I see. Okay,
Yeah.
no, but you're not lost.
No, not completely.
Okay,
yeah.
not completely.
Respond to me.
What was it? Sorry.
No, I had James respond to me.
Oh, okay, good.
Right now. Yeah.
Okay.
I'll tell him that his question is answered.
Okay. Right. So there is one difference though between the two versions. Now, if I with the first version, no, if I write S of well, let's say 10, that's correct. With the second version, I can't write S of 10. And I'm going to ask Mikhail for the reason. Why can I? So this is, let's say that this is version 1.
Yeah.
And this is version 2. Why is the S10 in the version 2 not syntax, not grammatical? Do you have any idea?
No, I'm not sure.
Okay. Well, I'll give you a clue. Take a look at the number of arguments that the number of template parameters that the two versions.
Okay, so the second one takes in 2 arguments. Is that
okay?
The reason?
Right. That's true, which means that this has to be something like S of, for example, int and 10. Right?
Okay, yeah.
Okay. Now, in the message, Daniel, that James gave you, did he say why he's not still in?
I'll have a look. See, but he has worked all night and
that's
hasn't
fine.
been able to recover.
Yeah.
He's asking if it's recorded.
Well, Hopefully he will watch the recording. Right. Okay. Now, so I told you that you know, these names do not escape this scope, right? So if there is no dependency on the latter ones to the former ones, then we can simply drop them. So that these two versions, they are equivalent. And if you pay close attention, you will notice that the only difference is that these two that are available to the left are not available to the right. Right? Now, at the bottom of this slide is a question that I have to some extent, you know, answered for you, but I will leave this as an exercise. So what if in this body, right, I want to have access to this type? How do you provide that? Now, this is a question that you might be able to answer gradually, but I'm not expecting you to be able to do that now. But you should be able by the end of this this semester, right? Okay. Now, template parameters can be packs, as you know, right? So, for example, you know, I can have a class called multi-array that takes that is a multi-dimensional array of type T, right? Which then allows me to you know, define a 3x3 matrix of type double like this, and then well, just like that, template parameters can also have packs, right? So, but the syntax is the one that you see on line 11, with the correction that I have applied underneath. Right. So you know, here what it is saying is that, okay, this this containers pack of parameters are themselves template parameters, and each of those take two template parameters, two type template parameters. Okay, I'll give you 10 seconds to watch this in peace and try to sink it in. Okay. 10 seconds over. Any questions with the bizarre syntax, like always?
It looks fine.
Okay, very good.
Actually,
Very good. So you managed to decrypt it. Okay, very good. Very good. Okay. Now, so parameter packs need to always come last. So, for example, you know, this, let's say that we are trying to do this last type thing. You know, it's a class template that wants to be variadic, right? Now, this last template parameter that it takes is not variadic, whereas the previous one is variadic. Now, this is not allowed in C++, and the reason is that the philosophy is that when you provide variadics, whatever that remains is the one that can vary, and the compiler will take whatever that remains as the variadic template argument, right? So if you switch between the two, well, then the semantics is different, and you probably will give it different names, but fine. So if you switch between the two, that's fine, because then the pack comes at the very end. Now, however, if that's when you want to explicitly pass your templates. Now, you probably remember that for function templates, we had template argument deduction, right? So in the case of this function, because the value parameter at the value level can be deduced, well, the type of it can be deduced. You are not required to provide that. And so if I just say run tasks of a few types, let's say, I don't know, float and string of 14, right? Now, the compiler will be able to utilize this to figure out the type T. And so these will be the test types.
Yeah.
Okay. Now, so, however, there are ways that you can kind of work around this necessity for the pack to be at the very last. So let's say that you have a class template called tensor. You can have a function compose that takes two tensors, and each of these can have its own pack because this is a separate parameter, this is a separate parameter, and it's for the compiler to figure out, according to template parameter, to template argument deduction, which values these are. Right? Now, so that means that then you can have like two packs at the very top, and that's it, no problem. You're allowed to have, it's not that only the pack at the very last is now acceptable, because you have now boxed the packs inside these names. Sorry.
Wow. So like the complexity really went up quickly there with
yeah, my apologies.
The template, and so
Yes.
you get one layer effect, and then adding variadic with it is like, and then these separate rules.
Sure. Now, if you're good with this, we can proceed. Otherwise, I'm glad to wait for it to even sink more.
If we could wait 10 seconds, that was
Is it? I mean, yeah. Is there any place where I can help, Mikhail?
Well, it makes sense, but it's a lot.
Yes, that's I
Yeah.
can definitely agree with that. It's a lot. It's a lot in just one go. You're right.
But yeah, you can proceed. I think I took a snip of it as well in case I want to look at it.
Okay.
Yeah.
Now, okay, this is for when I had already had practice sessions, which we didn't have the pleasure of, but we'll get to later on during the day. Now, pack expansion is when you have a pack and you want to use it elsewhere. And we've seen some of that. So let's say that, for example, I have this class called tuple that is variadic. Sorry, there is. Why am I? Okay. That is variadic. Sorry, is a variadic template. So if I want to have like a special another tuple class that is called my tuple, which inherits from the tuple class on line 1, and recall that this is the inheritance keyword, right? Now, in that case, we need to provide the template arguments that the class tuple is expecting. Remember that this pack then needs to be unpacked here by providing the ellipsis after it. Right. Yeah. So provided that the T's that we submit to tuple has size has length 2, and this is the notation for figuring that out.
You don't like using the vertical line?
I don't like using what lines?
No, usually when you want to denote the size of like a set, you use vertical lines.
No, this is not a matter of me liking it or not. This is a piece of C++. So in C++,
okay.
Yeah, there is this keyword called size of, which it inherits from C, which gives you the size of a variable. There is another keyword in C++ from C++ 11, I believe, that is size of ellipsis, so size of ... that you can use for acquiring at compile time the size of parameter packs.
Okay.
Which
So
I had taught you in the previous sessions, but that's fine. Now you couldn't recall that. Yeah, that's fine. Now, provided that size of ... of TS is 2, lines 3 and 4 here would be equivalent to lines 1 and 2 here. Okay. If it would have been 3, then lines 3 and 4 here would have been equivalent to this line 1 and 2. Okay.
Cool.
Now, remember that this one is a variadic template notation of C++, and so is this and this. But these, this is just, you know, me saying that there is something inside. This is not C++, right?
Okay. Yeah.
Good. Now, so the same goes with template specialization. So if I now have another tuple for pointers to t's, right? Now, then provided that the length of the number of items in the pack that I pass to t's is 3, lines 1 and 2 above would be equivalent to lines 1 and 2 below. And one thing to notice is that in the pack expansion, this you know, star sign for pointers sticks to the name that comes to the left of it.
Oh.
So this is not, for example, sorry, this would not expand to, for example, T1, T2, T3, and then a star sign. No, this is wrong. All right, the right one is this one, where the star sticks to the running, let's say, to the running name of the pack expansion, and then the pack expansion takes place.
Does it have to be placed afterwards, like between the ellipsis and the type? Or is it?
No, for example, well, it has to be valid specifier. So, for example, if it would have been, let me give you another example. If this would have been const t star, then it would have been, oh, what did I do? Then it would have been const t1 star, const t2 star, and const t3 star.
Okay.
You know,
right.
The qualifiers stick to the running name, and then the pass expansion happens. Right. So let's see. Now, pack expansion can happen at a good number of places. I'm only going to show you 3 out of the many, and I'm only going to briefly do so because, well, we are not going to touch a lot of that in the practice sessions. Here are those 3. So let's say that our class point is a variadic template, variadic class template, right? So it takes a variadic template parameter. And so one place where it can use that is in the definition or in the declaration of its parent classes. So it can inherit, it can inherit from all its template parameters. And it can do that because this is one of the places where we are allowed to expand the pack by putting the ... or ellipsis after the name here.
Okay. If sorry, this is lots, but to take argument, I'm wondering. Here they will all be public inheritance. Would there be a way to unpack this and choose? You know, maybe you want to have some privately inherited or protected.
Yes, you
Would that be
can.
possible?
Yes, 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 you can. You can replace this by private.
I assume that would affect. That would be then all. You know, all the inheritances would be private.
You want to do selectively.
Well, just for the sake of argument.
Sure. No, I don't think that is possible.
No.
So you want to selectively inherit from some of them publicly and some of them privately.
I'm just trying to think of, you know, how, you know.
Yeah, well, you can do specializations if you want, but that's not. It doesn't have a direct. It doesn't have a direct linguistic support.
No.
Yeah. Okay. Now, the other place that you can do that is in the initialization of the class. So this is, you remember that, you know, I told you that you can initialize a class in its constructor by placing before the body of the constructor and after the name of the constructor by placing the initialization things after the colon. You know, here is another place where you can do pack expansion, which is trying to this is trying to invoke the default constructor of all of the template parameters that point receives. Right now, another place is in the calls to functions. So, for example, here, you know, what it is doing is that it's providing this, you know, running name and then expanding that. Now, let's say that the size of, size of mixins, size of mixins equals 2. Right? Remember that all of these stick together before expansion. So this would expand to a visitor of static cast of mixins, one reference of this and static cast of mixins to reference of this. Sorry. All right. So, like I tried to say, you know, all the qualifications, all the running statement, running expression sticks together before expansion.
Okay.
Right?
Yeah.
Yeah. So then you can, I mean, these lines you just read on your own. It's not a big deal. Let me see. You can also have multiple pack expansions. Now, so let's say that your function takes arguments variadically, the types of which are also type level parameters that are variadically provided. So now I have values. Each member in the pack of has the type reference to constant over T, which itself is a pack at the type level. Now, in that case, so provided that size of this, for example, is 2, this is only example, right? Let's say that we have size 2, then this would have been these 3 lines at the top would be equivalent to the 3 lines at the bottom.
Okay, right. Yeah.
So it starts by giving these 2 at the type level to the function. Then one thing to notice is that it then expands the second pack, well, that of values at the value level.
Mhm.
And you see that the types here have the same indices as the values, because values expands according to T's. Right,
yeah.
and therefore this correspondence is also valid. Now the complexity doesn't stop there. Now someone had already said that this is a lot. Yes, this is a lot to take in at one go. That's true. But that's what we do in C++. We torture C++ programmers. Right.
Well, I feel like my head is getting packed as well, just like all these functions took place. I think.
Right. Now, let's say that you have a class template called nested that takes a variadic template parameters, and within that class you have a member function called f, which itself is parameterized variadically, right? Template parameterized variadically, right? Now, then let's say that you want to call another function g in the body of your yes, sorry, in the body of your function f with the types that you receive here being instantiated using the values that you receive here. Now, then you perform 2 pack expansions. And so let's say that the outer one has size 2 and the inner one has size 3. Then the code at the top is equivalent to the code at the bottom. And that looks like a Cartesian product of the 2 pack expansions. If you're familiar with that term, Cartesian product. Yeah. Now, I'll give you 30 seconds to help yourselves with the supposedly equivalent at the bottom.
Okay. Just to wrap my head around it.
You give me the go as soon as you're ready. I think this is the very last.
Yeah, I hope so. I've been stressing
Right,
out looking
yes.
at their power percentage.
Yeah. Yes. Yeah. This is the last slide.
But it seems okay.
Yeah.
Very
I
good.
like the dot dot dot.
Uh-huh. Yeah.
They're clear to understand somehow.
Very good. Very good.
Yeah.
Okay. Now let's stop the presentation before this guy dies and get into code. Now, I had asked you to take a look into an old or rather ancient posting of Bartosz Milewski, who is this physicist who has come to learn some programming and well, he has interesting blog posts, although he shouldn't be taken as a knowledgeable source for computer science. He has self-taught a lot of programming and he's doing great in some of them, but because he was never he never received any formal education in computer science, every now and then he makes plain wrong statements about programming and all that he just doesn't understand because he just doesn't have the right background. But the post that I sent you is sound, and so you can enjoy some of it. No, you can enjoy all of it, but we're not going to do exactly what he says.
Okay.
But that's a good basis for what we are going to do in our practice sessions, as I'm going to start right now, and also the project that we're going to have. Right.
Okay.
Now, so we'll start by are these readable enough to you? Let me see what I'm.
Yeah, good.
Okay, very good.
I will have to put my laptop on charge real quick, so
that's fine. Now, so Mikhail, do you have your editor and
Yep.
Yeah, very good. Okay. Now I'll also wait for Daniel to do his charger. Okay. Do you have your editor and compiler ready?
I do.
Very good. Very good. So now let's say that we would like to write a factorial function that is compile time. Now, before C++ 23, when there were no const eval functions, the only way to do that was to have a const expr function and pass compile time values to that function, right? Now, after C++ 23, we can make the function const eval, which means that we can enforce the function to be only applicable at compile time. Even before that, prior to C++ 17, where there was no const expr, the way you would have done that would have been that you would do what is what used to be referred to in C++ TMP as the meta functions. Now this is not official C++. This is colloquial C++. Right? Now, when C++ TMP people would speak about meta functions, they essentially mean structs or classes that either have something called value, right? Or something called type. If I can show you, no, there is nothing here, but I can show you something else. Right. So like this one, for example. Right. Now this is so the previous one. Right. This is when the meta function is so-called returning a value. This other one is when the meta function is so-called returning a type. Now, there's no returning really here or there, right? This is only specification. There is no function call is taking place here. And therefore, there is no return really, right? Now, let's get back to the value case. Now, the way you do that in well, for the value, for when you're returning values, and this is, by the way, these names, value and type, they are conventions between the C++ people, right? There's no restriction by the compiler for this to be called value. These are conventions between the C++ programmers. It's a human-to-human convention. It's not a human. There is no computer in the loop, right? Now, so the convention is that when a meta function is returning a value, and this is just returning within the double quotes, right? You would do the returned value for the reasons that I have already explained, and I will get back to shortly. It has to be a static const expr, and then the type of that value.
All right.
Now, in this case, we have chosen that type to be unsigned, which means unsigned int, right? Now, why static? Because we want the value not to be a member function, a data member of a specific instance of this class. In fact, these classes are not designed, even though technically you can instantiate them, they are not designed for instantiation. Right? They are only designed for being used as well, statically. Right. Now, so that's why you get the static, because a static data member does not belong to instances. It belongs to all the instances of the class or struct. That's one thing. And we are enforcing that to be available at compile time by putting this const expr here.
Yeah.
Right? So that's this. Now, other than that, with all the syntactic noise that you receive, I think the logic is relatively obvious. You know, what it says is that factorial of 0 is 1. Factorial of other n's is n times factorial of n minus 1. Right?
Yeah.
Now, this thing itself, factorial of n minus 1, is a class or a struct, right? It has not still been evaluated. It will be evaluated only. So the meta function is not still the call to the meta function is not still evaluated at this point. It will only be evaluated when I require something from that meta function, which is me, requiring the value static data member of that thing. So this is what I meant. So I'm again getting back to James here. This is what I meant by lazy evaluation involved. So fact of n minus 1 is kind of like binding n minus 1 to the meta function fact, but still not performing the function call. The function call is only performed when you enforce it by acquiring the value data member, the value static data member of the function call. And I should rather say meta function call. Right? Now, so the strange thing here is that, so by default, that means that template metaprogramming is lazy, but it provides selective strictness, whereas that's the practice. That's the practice is that you almost entirely want to selectively enforce strictness, and only sometimes you may in practice just go lazy, right? So the thing is that it's by the nature of C++ template metaprogramming, it is lazy by default and provides selective strictness, but in practice it's strict by default with the provision of laziness, selective laziness, right? So it's a very unorthodox combination, right? Now this is and by the way, this is orthodox with the little o, not with the capital O. Yes. Now, so I would like to ask you at this point to put these lines into your own editors for me.
Already done.
Very good. Yeah.
Oh,
Okay.
I'm the line now.
Just one question.
Tell me.
What does the auto before the end do? Because that's the one expression I don't understand.
Okay, very good. So what this is saying is that n can be of any type that is acceptable here.
Okay, so it's okay.
Pilot use.
So for example, this can be unsigned. It can also be int. It can also be well, from C++ 23, I think, or is it 20? It can also be like float.
Any type that supports the operators used within the function.
No, not that. Any type which can be, values of which can be passed as non-type template parameters.
Okay.
Okay.
Yeah.
Thank you for asking. I see. So did you get to watch the previous recording?
Not yet. I was planning to do
Okay.
it in the weekend.
Right. I see. Well, I think I have explained that in there.
Okay, great.
Yeah. Daniel, are you done with the?
Sorry, sea lion is taking a long time to do up. It's
Oh, I'm not surprised. I'm not surprised. Yes.
yeah.
Yeah, I mean, it's the
I-
load of sea lion is famous for that. Yes.
Normally I tend to just I enjoy coding on a simple text editor. I use
Right.
Sublime or something similar, and then just wrestle to the terminal.
Sure.
But,
Sure.
okay.
Yeah. I mean, this code blocks is a relatively lightweight editor. So, and it's not as powerful. It's not as powerful as Sea Lion, I have to say. But
No,
but
but
it's quite lightweight.
exactly, and you don't get pop-ups of wanting to add a Git file and
Yeah.
you know, all sorts of rubbish
Sure.
around for type quickly this in. Okay.
Now, Mikhail,
Yeah.
so you are done with writing of this, and I'm just gonna do something else. Let's say that I place this here. These are not a part of what I'm teaching you today, so I'm gonna comment them for now. Now, I now would like to ask you, Mikhail, and later on Daniel, to do things like this. So let's say that we have, let's say that we do namespace standard, which you shouldn't, but just to be quick, I can do things like fact of 10. Right. Now, could you please put this in, Mikhail?
Yeah.
Okay. And then compile your code, please.
Just let me remove the basic.
Okay. Well, my
and you can forget about this one, by the way.
Yeah.
So I'm going to compile now.
Yeah. Sorry, my editor is crashed.
What was it? Sorry. Your
My
editor.
editor has frozen.
Ah, it's frozen. Oh, I'm sorry. Okay. Well.
Nope.
Sorry, my
Copy now.
bad. My bad. Mikhail, I had given you the wrong syntax. Just notice that I changed line
Yeah.
20. Yeah. Now, Daniel, are you now putting the C++ in?
I'll make you over.
Huh. Yeah, I'm getting some errors.
There you go.
Okay. Will it compile for you if you just put these in, like lines 5 to 15?
I'll check. Yeah, it's
It
the
does come. Okay. Have you got the IO stream included at the very top?
Yep.
And you have this using namespace dude?
Yep. It's mad that the cout what are those symbols of the cout called in English again?
That's shift left.
Yeah. It's mad at those for some reason, so I'm confused.
Can I see your code, please? Would you mind sharing it?
Sharing my screen? I
Yes,
can't.
would you you can share your screen. You should be able to.
It says you cannot start screen sharing while the other participant is sharing.
Okay. Well then I stopped sharing.
So oh
Right. The well the trouble is on your line. Yes, those pair of parentheses after fact of 10 are extra.
oh okay. That easy.
Yep.
Ah.
Yeah.
And yeah, that
Yeah,
seems
you get to your
about right.
Yeah. Yeah.
I've got the same. I've got the same.
You got there too?
Yep. Yep.
Very good.
Yeah.
Now, here's something I would like to show you in let me just get back to my sharing. Now, let me say that I just copy paste this into Compiler Explorer. Now, so, and let me just remove what we don't really need. Right. How much assembly do you two read?
Only 9 lines.
Okay. Now, fine. What I would like to draw your attentions to is that, first of all, this assembly is very little.
Yeah.
Yeah.
Right?
Okay.
The other interesting thing here is that this is already hard coded in your assembly.
Cool.
Do you know why?
Yes, it's compile time.
Aha!
Yeah.
That's it. So this is the point at which you finally got to see it with your own eyes, that when I say this is compile time programming, I'm referring to this, which means that literally the runtime of this piece of code is 0. Right? So let's get back to the
benefit now.
Yeah. Let's get back to here.
See the difference without the context of what the assembly would look like.
What was it, sorry?
Like, can we see what the assembly would look like if we did not make it compile time? So remove the context.
Well, prior to C++17, you would call these const, which would still be compile time metaprogramming, right? But you know, the things which you would then be able to put on the right hand side, which would be well, more restricted, right?
Okay.
But anyway, this is equivalently compile time for this very example. And in fact, I think that Bartosz Milewski in his post I think he has this, if I'm not mistaken. Now, maybe he doesn't, I don't know. But in that time, so his code is prior C++ 11, right? So he doesn't have a const expr. And he uses like static consts for that purpose, right? Now, another thing that I would like to show to you is this new website that I hadn't before shown to you called C++ Insight. And for some reason it's not here. Okay. All right. Now C++ Insight is interesting because it shows you the unsugared or the desugared, sorry, the desugared version of your code. Right? Are you familiar with the term syntax sugaring?
Yeah, like the
Daniel?
arrow syntax.
What was it, sorry?
Such as the arrow syntax.
I can't hear you very well.
The arrow syntax.
The arrow
You know,
syntax. Well, I'm not sure what you mean by the arrow syntax, but
the C out and then the left arrow or left shift or what it's called.
I see. No, it's about, you know, it's so have you have in the past seen me saying that, you know, this is a shorthand for that other thing?
Yeah.
You know, the compilers provide these shorthands, and that is referred to as syntax sugaring. Right? Now, when you write in the longer version, you are said to be desugaring your code.
Pointer arrow. Oh.
Yeah. Now, right, the pointer arrow syntax. Yeah, well, for example, yeah, you're right in that. So the arrow syntax is a sugar for dereferencing and then applying the dot. That is true. Now, if you replace the arrow, the right arrow, by a dereferencing in parentheses and then you know, making a call to a member using, sorry, referring to a member using a dot, then you're desugaring your code. Now, C++ Insight is great for doing that. So if you do so, that this is our code as I had put in our C++ compiler explorer, and then I press this, the play button. It shows to me that, okay, we had a primary template function, template struct template or class template called fact, but then, you know, in the line 6 here, which is this line, we recursively made calls to these ones. There is a, you know, we made call to fact of 9, which in place, let me get this to the bottom. Well, which in return makes a call, and this is call in you know, double quote, right? Call to fact of 8, which itself is a specialization of fact, which in return makes a call to fact of 7, and so on and so forth. It shows you all the specializations that your code makes until the very bottom, when it gets to 0. And this 0 thing is something that our code itself has provided. Right? Now, this is a great tool for, you know, when you're working with templates, you want to see how does the, you know, well, this is out of context terminology. But if you want to see the call graph of your meta functions, which in reality would be the instantiation graph of your class templates, C++ Insight is a great tool. Now, here is another interesting desugaring, which is unrelated to templates. So you spoke about, Mikhail, you spoke about the shift left operator.
Yeah.
So the equivalent of this guy is what you see on line 112.
Yeah.
Okay. So that should be all for today. And we're already 6 minutes past. So I'm going to now stop sharing and stop recording.